Hi and welcome back. This tutorial will be all about blueprints and what is inside the blueprint graphs of all the most important blueprints in the toolkit. That is quite a lot of stuff actually, so this video will be pretty long. So I will link to the different time points in the video where I speak about the different sorts of blueprints. So you can check that out in the description below. Now I've waited for a while and put off making this video because I've made a lot of changes to the blueprints. I've had a lot of updates that has changed a lot of stuff around. Now this will continue, so I might as well make this video now, and I will add in annotations any changes I make in the future, so make sure that you view this video with annotations enabled. So first I will quickly describe roughly the functionality of the most important blueprints, and then I will go into them in detail. All the important blueprints are contained within, big surprise, the blueprint folder here, and most of the big ones are in the gameplay folder. So here we have a lot of the important ones. So we are going to start with this one called ATBT, Advanced Turn-Based Tile Toolkit, Game Mode. Now the game mode sets up the game in the beginning through its event graph, and it spawns the grid camera and the AI controller, and it sorts pawns in initiative order. So this game mode holds which pawn is the current pawn, which is the next one, the initiative, and it also holds all the functions that ends the turn of one pawn and starts the turn of a new pawn, whether that's an AI pawn or a player controller, and it sends that message over to the player controller or the AI controller depending on what faction the next pawn in initiative is. So this is what we're going to look at first, and then we have the player controller, which controls all the input of the player, from clicking to just hovering the mouse over a tile. The player controller holds all that, and it decides what happens when you click a tile, whether to attack, whether to move, all of that. Then we have the AI controller, which does much of the same stuff for the AI, though it has a lot of decision trees and logic inside to decide what actions one of the AI enemy pawns does during its turn. Then we have the grid camera, which controls the movement of the camera, so it also handles input, but only for moving the camera around, panning, rotation, zooming, all that. Then we have the grid manager, which is pretty all important for this toolkit, since it spawns the grid and it holds all functions that has to do with the grid. That includes pathfinding, checking for visibility, when you click a pawn, how does the toolkit decide what pawn has been, tile has been clicked, and so on. So a lot of these other blueprints reference this grid manager. But I will start describing these, and this will mean that I will have to describe some of these functions briefly, but I will go into the functions in more detail later on in the video with the grid manager. Then there are a couple of other important blueprints that are inside separate folders here. For pawns, we're going to look at unit parent, which controls the units and moves them across the board. Decides when the movement should be stopped, when to attack, all of that, though it gets most of its input from the player or AI controller. And we're going to look at one of these other pawns as well, since they have a bit more functionality in regards to animations. And we are going to look at tile parent, like the base tile blueprint, which is the parent of all the different tiles that you can place. So looking at this, you will hopefully understand how all the other tiles work as well. So that's what we're going to go through. So that's quite a lot of stuff. Yeah, let's start with game mode. Though on second thought, maybe we should start with the grid manager, since that's sort of the heart of the system, and all the other blueprints reference the grid manager. So yeah, let's start with the grid manager instead. This is by far the largest of all the blueprints, so this will take a while, but you have to start somewhere, so let's start with the grid manager. So there's lots of important stuff happening both in the construction script and the event graph of the grid manager. Let's start with the construction script. So I will try to keep this at a reasonable level of detail. I can't go into too much detail or you'll listen to me drone on for ages and ages, but I'll try to explain enough that you'll be able to figure it out, hopefully, the details on your own by looking at it. Though if you're still stuck, feel free to comment on the video below or leave a comment in the forum thread on the Unreal Engine forums. And I will try to answer you as quickly as I can. So, the grid manager, what does it do? So, the construction script, as you know from using Unreal Engine, the construction script code is code that runs in the viewport. So this all happens even though you haven't pressed play or you aren't playing the game. So the first thing it does is make an instance static mesh component of the default tile instance. So it makes an instance static mesh, which is this static mesh, and chooses that at the start of the game so it can be referenced later. And the visibility is set depending on the show default tile public variable. So should this grid be visible or not? And that's the first part. Then it decides what to do depending on what we've made the default tile object to be. So the default tile object can be, as you can see here, it can be an instance static mesh, as it is in this case. It can be a texture, let's see, like this. It can be a static mesh, like this, which looks identical to the instance static mesh, but is less efficient, but might be necessary in some cases. Mobile games don't allow for that many instance static meshes. But in any case, these three, so here it decides what to do depending on these. If you have an instance static mesh, then it sets the static mesh of that instance static mesh to the default grid mesh, which is set here. So it takes this public variable and puts it into here so that it knows that this instance static mesh component should look like the default grid mesh. And it decides the tile bounds and of the grids depending on the size of this mesh. So it looks at the bounds of the mesh you have put in, and it sets these values to be equal to those bounds. So in case of the regular square tile, these will both be 200 Unreal units. So from now on, the toolkit knows how big the tiles are and can use these and doesn't have to check the local bounds every time. Then it makes the gap between tiles in the y direction smaller for hexagonal grids. As you can see on a hex grid, the distance between two tiles like this is larger than if you go directly up like this. So the distance here is smaller, so it takes this number 0.86603, which means that it will work for a hexagonal grid. As you can see, if it's a hex grid, it does this. If not, it just keeps it as it was before. So yeah, before we go to the next part, we'll look at the texture bit. So if we have a texture instead, then it sets the bounds depending on the grid texture size public variable instead of getting local bounds. It creates a dynamic material instance. So this makes chooses the size of the texture basically that makes up the grid for a texture grid. Then we go here and then we scale and position the collision plane. So the collision plane, let's see, let's show it again. There we are. It's this plane that detects collision, so that we can detect when we click a tile. And we don't have to have a collision for every separate little tile, since that's less efficient. We just have one huge collision plane. And that's also a component, by the way. Well, it should be. Yeah, there it is. which is not visible by default. And let's go back to the code. This is where we resize the collision plane and place it appropriately in relation to the grid. So we have this set collision plane scale and location. I won't go into much detail in this, but it makes the size of the collision plane depending on the tile bounds, whether or not it's a hexagonal grid, and so on, and scales it appropriately. Let's see. And decides visibility, depending on whether we've decided to show the collision plane or not. Then we create the vector grids. So as it says, these form the basis of moving between grid array indexes and word locations. So this is where we set up the relationship between array indexes and locations in the Unreal editor. So this is where we set up so that, well, this tile is index 0, this is index 1, this is index 2, and this has location 0, 0 in this case. This has location 200, 0, 200 in the x-axis, 0 in the y-axis, and so on. So the grids are set up so that this is index 1, index 0, index 1, index 2, index 3, and so on. And then we go here, this will be index 20, since we have a grid size of 20, 21, 22, this will be 40, 60, 80, and so on. And this is set up here initially. So first we decide whether it's a hex grid or we check whether it's a hex grid or a square grid, because this will be important for the y-axis, since the distance is smaller for the y-axis, or shorter for the y-axis than for the x-axis. And they are also, as you can see, each row is offset, so it's different for odd and even rows for a hex grid. So hex grids are a bit more complicated. So let's start with looking at when hex grids are false. Then we take a for loop first, which is for loop that is the size of the grid. And the size of the grid is naturally grid size x times grid size y. As you know from basic math, this will be the size of the grid, and then we subtract 1 because this starts at index 0. Just to take that into account. And then for each of these indexes, so this will start at index 0, and the last index will be this times this, as you can see, and we put it through this this function called index to vector square grid. So here we do some simple math to turn the indexes into vectors. Now, so for the x location, we do a modulus expression like this. And if you don't know what modulus is, you should read up on it quickly. But basically, if we have grid size x and we have index 5, grid size, I mean, the grid size is 20 and the index is 5, then it will return 5. If we have index 25 and this is 20, then it will also return 5. And then we multiply this by the tile bounds, in this case is 200. So we know that if we have a tile that is at index 25, we get 5 here, and then we multiply by the tile bounds, which is 200, and we get 1000. And this is the location, the x location on the grid. For the y location, we simply divide the index by grid size x. And do the same to get that location. And then we add all of these into the vector field array. So from this point on, if we want to know the location of an index in the viewport or in the game, then we can just get that index from the vector field array. So we don't have to do this anymore. From this point on, hex grids, it's much of the same, but it's a bit more complicated. So it does the same things basically, but it must take into account here that odd and even rows are slightly differently spaced, so we have to offset them by half the tile bounds x on odd rows and not on even rows. And also for the distance on the y-axis we have to multiply it by 0.75 since the distance, like I've said before, is shorter. And we make a vector array for this as well and store it in the vector field array, so that works the same way. Then we do the actual spawning of the grid. So we check if we're going to show the default tile. If we are not going to show the default tile, there's no need for showing the grid naturally, so we just go to the next. But if we do, then we check what kind of object did we have again. So if we had an instant static mesh, let's see. And yeah, this is a little extra things to see if we want to have a rotator array to rotate, so we can know the rotation of each of the tiles. This can be set also as a public variable, so whether or not to make such a rotator array. But then we go to the vector field array we made earlier, and for each of these locations in the vector field array we place one of these instant static meshes, and we make a grid like this, so pretty simple. For static meshes it's very much the same, only we add a static mesh component instead of an instant static mesh component. Now for textures we also just go straight to the next part, because the textures use the collision plane instead of placing any meshes, so we don't need to place any meshes there. So we go to the next part, and now we check if we're going to pre-generate gameplay grids. So this is a thing you can activate to have the game load a bit faster than we pre-generate, but it's a bit slower in the editor with this set to true. But let's look at this. This generates some of the important grids that we use in the game beforehand, since we know what the size of the grid is going to be. So this resizes 3 important arrays. I'll get into these in more detail later, but I'll describe them briefly. So the pawn array knows the location of all pawns. So this stores the faction of each pawn in an array that is the size of the grid. So for instance, on this tile, if we get the index here and we check the pawn array, it will return enemy, because that is the faction of the pawn standing on that index. If we check here, it will return player. If we check here, it will return empty. And now we have the can move to array. This is important for pathfinding. It stores whether or not the current pawn can move to any particular tile. And then we have the pawn actor array, which is kind of similar to the pawn array, though instead of storing the faction of each pawn, it stores the entire pawn. So if we check this tile index, we would get this specific pawn actor. Now why not only use the pawn actor array and just not use the pawn array? Well, because it's quicker to check this array, so it's useful in cases like pathfinding, where we want to check lots and lots and lots of different tile indexes for pawns. But you can use this for everything if speed is not absolutely essential. And then let's see, we also make an edge array. So the edge array holds the edge costs of all indexes or all tiles. So the edges of this index would be 1 in all directions. It stores a lot of or 6 indexes for hexagonal tiles. For this we can see the edge cost of this is 0, so it's 0 in each direction, and so on. But this first sets up the costs for the default tiles. So if we have set the collision plane to be walkable, then we set the edges of all tiles to 1. If it's not walkable, then we set the edges of all tiles to 0. And if we've set it all to 1, there's a function later that makes sure that all the walls have edges that have a cost of 0. That comes later. Okay. So after we've done that, we have this special instantiate part that gets all tiles that we've set to be instantiated and turns them into instant static meshes instead of being actors with static meshes. This is a bit complicated to get into, so I think I will skip it for this video, but if there's interest I will go into it in more detail later in a different video. So that's the construction script of the grid manager. So the event graph of the grid manager looks deceptively simple, though there's quite a lot going on here inside of these functions, and even more inside these functions here and these macros, because the grid manager functions much as a function library for the other blueprints to call. But let's start with what's here in the event graph. So at begin play, we first check if the collision plane should be walkable or not. So if it's walkable, we set it to block path trace, which is the trace channel we check to see if a tile is clickable or not, or we set it to ignore if it's not walkable. So if it's not walkable, we have to place manually all tiles we want to be walkable, as I've talked about in the previous video. Then we check if the gameplay grids have been pre-generated or not. If they were not, we have to generate them now, so we do that. That's the same as in the construction script. Then we check if snap to custom grid is set to true. As a reminder, this is snap to custom grid. If it's not true, then we can move these freely around, while if it's set to true, then it will snap. But as you can see, the center of the actor is actually not the center of the mesh. So this isn't too important for these tiles, but it's important for the actors. Because it will move strangely and always be on one side of a tile when it moves. So we have to make sure then that all the pawns grid anchors are equal to their location. So it basically does the same thing as when we click here, place actor at anchor, and make sure they are at the same spot. So that's what happens here. So we get the location of all pawns which have the unit parent class, and for each of them we get the world location of the custom grid anchor, and the custom grid anchor is always in the center of whichever tile the pawn is placed on. Then we place the actor on that location, and after the actor is placed, we place the grid anchor at that location as well, and then it will be centered. Let's see, so that's that function. Then we add the viewport terrain to arrays. Now this is a big function, lots of stuff going on here. So yeah, I guess I'll just have to start to describe it. So a lot of stuff happens here, and it depends a lot on what you are and what options you have enabled. So first we check to see if height map is enabled, and if it's enabled from tracing. I've mentioned this in an earlier video, but this is an option that traces on all tile locations on the grid and checks to see if it hits anything on the way down that blocks path trace. If it does, it says okay, then the grid is this high on this location, and it stores the height of the tile that is hit. So if we check from tracing, then this is how we do that tracing. So we get the vector field array. That's the array we filled up with the location of all tiles earlier in the construction script, and for each of these locations we do a line trace, and the line trace is then done let's see, from the location of each of these vectors, and then we add the location of the grid manager itself, in case the grid manager is not placed on the location 0, 0, 0. And then we do a trace, and the start z, the height, is equal to the location of the grid plus the max grid height, which is a public variable we can set, and we do it to the minimum grid height. And if it does hit anything on the way down, so the return value of hit is true, then we first set the rotator array to the location, to the rotation of any actor we hit, and we set the vector field array to be equal to what it was before, except for height, which we now get from the hit result minus the location of the grid manager. And then for the edge array, we set all the edges to 1. So it's all walkable, at least initially. We will change that later on, perhaps, depending on the other settings. Now, if we don't hit anything on the way down, that means there's no tile there and it should not be walkable at all, so all edges are set to 0 in the edge array. So that's how we do that tracing. Then we go to the next in the sequence. And now we get the edge cost of all the tile actors that we have placed in the viewport, and we add them to the edge array. So for all actors of the tile parent class, that means all tiles, we check them. We check first if the collision plane is walkable or not. Let's see, I'll get back to that. If it is not walkable, then for each of the tiles that we hit or we have, then we set all the edges to 1 initially, or the rest won't work, as it is set up to assume that the collision plane is walkable. So this is a little workaround for that. But in any case, we again get all the actors, all the tile actors, and for each of them, see here, we decide what the edge array is going to be. And how do we do this? Well, we get first the index of the tile that we have hit. So the index of a tile is set here, as you can see. We get that index, and let's see. Yeah, so we get that index and we check on that index in the edge array. That means in this case the index or the edges of the underlying tile here. And we check and we get all the edge costs of that tile. And also we get the edges of the tile actor in question. So we get all these edges here. So all of these are 0. Since the default tile is walkable here, then all the edges of the underlying tile here will be 1. So all of these are 0, all the underlying are 1. And then since one of these is not walkable, that means that we don't want the tile to be walkable. So we have a little function here, and it returns the highest of 2 integers, or it returns 0 if either of these two are 0. So if either are not walkable, if the underlying tile is not walkable, or there's a wall on top that's not walkable, we don't want it to be walkable. If one of them has cost, like this one, cost that's higher than 1, then we choose the higher of the 2 costs. So yeah, you can look at this, but that's basically what it does. Let's see. And then for each of these edges, it sets that for the edge array. So you can have, of course, like these wall tiles that just block one edge. Yeah. And then it makes all the walls double-sided. So it checks, is it a wall? That means, is it 0 on this edge? And if it is 0, then it makes sure that the tile on the other side is also, the tile edge on the other side is also set to 0. So that means here, if this edge is 0, we also want this edge to be 0. So it checks all the surrounding tiles, and it sets them to 0 if there is a wall on this side. That happens here. Okay, when we're done with that, then we generate height map from individual tiles if height map is set to from tiles. So this is an option for height map, that you can set the height map to be decided from the height of the different tiles you have placed in the level, instead of doing tracing. In that case, it checks, it gets all tiles again, and it gets the height, the Z location of all these tiles, and it enters them into the vector field array. And it also gets their rotation and enters them into the rotator array. Then finally, for the last part of the sequence, we check if we want to create auto edge cost based on height, which I've shown in an earlier video as well. If we want to decide the edges or the costs, the edge costs for each tile, depending on how on the height difference between those tiles, so that if a tile is sufficiently high up, you will not be able to walk from one to the other. Now, if we do this, we have to do it differently, whether we have a hex grid or a square grid. Let's start again with the square grid, since it's simpler. So for then again, we get all the locations we have in our vector field array, and for each of them, we check all the surrounding tiles. We check 4 of the surrounding tiles. Let's see. Let's make this briefly a square grid, which makes it a bit easier. So for each and every tile, we want to check that tile, and then we want to check all of these 4 surrounding tiles, and we will check the height of this compared to the height of this. If the difference is too big, we want to set this edge to 0, and we do that for all those. We don't do that for the diagonal tiles, since that's not necessary for the pathfinding. So we check at array index +1, which is, since this is 0, this will be 1, right? Since if this is, say 8, I don't know, this will be 9, this will be 7, and this one will be equal to 8 plus grid size x, so it will be 28, right? And this will be 48, and so on. So that means that for any tile, we can find all its neighbors by getting its index +1, index -1, index minus grid size x, index plus grid size x. So that's what we do here for the square grids. As you can see here, +1, -1, plus grid size, minus grid size. And for each of these, we check the z differences, the height differences, from the index we are checking compared to the index, the parent index, so to speak. And we do a function here that checks the differences, and it returns a cost depending on the height differences between the two, which depends on the height impassable cutoff and the height slow increment. It will take too long to go into that in detail, I think. Let's see, but I lost where we were. There we are. So we find the cost, and we enter that into the edge array. And since this is +1, so that's the tile to the east, we want we want to set this cost to all the west edges. That I guess that doesn't make sense initially, because we're checking this, we're getting the height difference between these two, but we're modifying the edges of this tile. So that means we have to set it to western edge cost, and also the northwestern and the southwestern edge costs of this tile, and then this tile, and this tile, and this tile. So that's what we do for all the western ones, and we set all the other ones that are not the west ones to whatever it was before, just the default, so we don't modify those. And then we do the same for all the other edges. So hopefully that's understandable, I hope. And then for the hex grid, we do much of the same stuff here, though because it's a hex grid, it's a bit more complicated. So we also check, now we check the one to the northeast and the one to the east and the southeast. So it's basically the same, but we have one here where we do it for even rows, and one where we do it for odd rows, since that will be different in hexagonal grids. I can't go into the difference between hexagonal grids and square grids in too much detail. I think that would take a long time, but I will link to some great tutorials on the subject by a guy called Amit, which will explain that a lot better than what I can in any case, and it would take too long. But yeah, suffice to say, you have to check. Yeah, you have to check it a bit differently depending on odd and even rows. So that's that. Okay, that's the function. And for the next, now we create walls on grid edges. Like I said before, if we set the collision plane to be walkable, then all of these tiles have all their edges set to 1, and we don't want that for the edges, because then the pathfinding will keep looking past this edge, and actually in the array the index that is 1 less than this is actually that tile. So if we don't have edge cuts of 0 on these walls, then the pathfinding will continue beyond here and enter from the other side, and that's not what we want. So we change the edge costs of well, the grid edges, like, yeah, the edges, in this case all the tiles located on the edges. So we check all possible indexes, and for each of them we check if they're on edge. So first we check if the index, we use a modulus with grid size x, is equal to 0. This means that all of these tiles here on the western edge will return true. Then we have to change the edge costs, and we do it slightly differently for hex grids and square grids, because for square grids we can just set all these edges here, all these 3 to 0, while for a hex grid, as you can see, for this we have to set all 3 to 0, but for this we only have to set this one to 0, while these two should not be set to 0. So it's slightly different for those two. And what might be confusing here, I just said we're looking at the western edges, right? But we're setting the eastern edges to 0. And that's because this is the cost of entering that tile from the east, actually. So, which in this case is this tile is trying to enter that one from the east, and it checks and it finds that the edge is set to 0, so it does not enter. So that seems a bit backwards, I guess, but that's how that works. Then it does the same thing, checking if it's on the eastern edge, pretty much the same math here, and on the northern and southern edges as well. That's how that works. Keep losing the event graph here. Okay, now it's time to add the pawns to their respective arrays. So we get all the pawn actors again, like we've done before, and for each of them we check their index values, which are set on each and every pawn. Oh yeah, now they're placed strangely because I've switched between hex grids, but yeah, no matter. But each of them have an index value in any case. And we get this index, and we want to set the pawn actor array and the pawn array. We have to update them with the faction of the pawn and the pawn itself. So we set the array element at that index for those arrays to the faction of the pawn and to the pawn itself. Yep. And finally we add the mesh components. The mesh components are these meshes here. All of these, we want to add them so that the toolkit understands that we want to use all of these meshes later on. And first we check if we're using decals or not. So if we are using decals, we want to add these decals instead of these meshes. So if this is true, then we first decide the size of the decals that we are using some pretty basic math here, and then we add each of the marker decals. So all of these markers that shows the current pawn or the hover marker, stuff like that, we set their scale as well. We're scaling them relative to the default tile, so we're getting the size of the decal component that we're using, and we're getting the tile bounds, and we're scaling them relative to these. So the default value for the tiles are set to 200, though I've done some small adjustments here to make them slightly smaller in this case. But yeah, it checks the tile bounds and scales them. And if we are not using decals, then we add a lot of meshes instead. So we add an instant static mesh components for many of these. For most of them actually. We have static meshes for some, but a lot of the meshes in this toolkit are used for multiple meshes that are shown, a lot of them at a screen at a time, so it's often better to use instant static meshes. So I do that for the tiles in sight range. So we add an instant static mesh component, we set this value to contain that instant static mesh component, and we set the static mesh of the tile in sight range material component to the tile in sight range mesh, which is the one we've set up in the public variable, and then we scale it relative to the default tile. Now it's saving. Should disable that for making tutorials. Well, it does the same thing for all the other tiles as well, for the tiles in move range, for the hover marker, for the current pawn marker, and so on. After it's done with that, we set our spline component. So the spline component is the spline that shows movement trajectories between pawns and their targets. So we add a spline component for the one that shows movement and one for the ones that shows range, for the ranged attack trajectories. And we set a variable called spline mesh length that's used in other functions later, depending on the tile bounds of our default tile. And finally, we add an instant static mesh component for if we choose to not display paths as a spline but as instant static meshes instead, then we set that instant static mesh here and set it to be the path mesh. Let's see. So it's pretty slow today. There. Here it's showing as a spline. And let's see. Here it is as a mesh. So that's where we set that up. Right. Let's Let's see. So there I think we've gone through all the stuff in the event graph. But like I've mentioned before, there's loads of more stuff in the grid manager underneath or inside these different functions and macros, but these are called from other blueprints. So I think I will describe them when they are called in their particular blueprints, since then it will make more sense for the context in which it is used. But so we will be returning to the grid manager in a sense, but this is what I will talk about the grid manager for now. So let's move on to the next blueprint. So now it's time to look at the game mode. So the game mode, let's see. So the game mode sets up a lot of stuff at the start of the game, and in later turns and also the first turn it chooses what pawn is to be the current pawn. And then when it has chosen a pawn, it decides whether or not to activate the player controller or the AI controller, depending on the faction of the current pawn. So that's basically what it does, but let's describe it in more detail. So at the start of the game, first we spawn the AI controller, and we set a reference for it, and then we find our grid manager. There should only be one grid manager in the game at a time, so it gets all actors and gets number 0, and it sets the grid manager reference to that value. So that will be set to whatever grid manager is placed in the viewport. Then it creates the HUD and adds the HUD to the viewport, and then we sort all the pawns we have in the game in initiative order. So this is a really simple sort algorithm, really. It puts all the player pawns first in initiative and then all the enemy pawns afterwards, and the order in which it does it is actually the order in which they were placed in the level. So it gets all the unit actors, set a unit parent here, and for each of them it then checks to see, is its faction a player, then we add it to initiative order. If it's enemy, we don't. And then when we're done, we do the same thing, only we look for enemies instead. So then all the enemies are added last. So this is a pretty simple one. There is another one which is unused, as you can see, that sorts pawns in the initiative order depending on an initiative value. So this is here, so you can add it if you want. Here I'm using the damage value to sort them, but you would replace this with a custom initiative value you would add to unit parent. But this works too, and you can just replace this one if you want to use that instead. There are many ways to sort pawns in initiative order, of course. And then we set the current pawn to be the first one in the initiative order. Then we wait for a little bit, and there are a few reasons for this. We have other blueprints as well that does stuff on event begin play. So we want to delay so that we're sure that all that has been updated before we move on. Then we spawn the grid camera in the level. Let's see, and we also set the camera to be the same transform, the same location as the current pawn. So we start by hovering directly over whatever is the current pawn. And we set up a reference. Okay. Then we find the faction of the pawn, which is the current pawn. We get the faction here, and we check. So if it's a player, we set player turn to true. If it's not, we set player turn to false. And if it's not the player turn, we disable input. We enable if it is a player. Yeah, and this is a interface call that calls to the HUD blueprint that just changes the little white text in the top left corner to either player turn or enemy turn. Yeah, I'll look into the HUD later. And it sets the grid camera ref to is panning is set to false. This means that it is not panning. The player is not currently panning the camera, and that means if follow cam is set to true, it will follow the current pawn. Okay, and then it checks the current pawn. Has the pawn acted this turn yet? That's the value within current pawn. And if it has already, that means that we have gone through the entire initiative array and are at the start again. So then, in that case, a new turn has started, and we make sure that, let's see, that has acted this turn value is set to false, and we add 1 to the turn counter. Actually, this kind of doesn't make that much sense when I look at it. I think this will add to the turn counter for every pawn on the next turn. Well, I'm not using the turn counter for anything yet, but I'll have to fix this before the next update, if I'm right. But in any case, the basics will be the same. And then, afterwards, when looking at, now it looks at, is it the player turn? Which means, was the pawn that is the current pawn now player or not? If it is the player turn, then we set the visibility of the hover marker, which is what is hovering under your mouse when you're hovering over a tile. We set the visibility to true because we want to see that on player turns. On AI turns we don't want to see that, so we set it to invisible. And then we get the player controller and we activate unit, which is a custom event inside that controller. If it's an AI, we instead wait for a second, just so that, well, if this is just looks better if the AI waits a little bit before they start running. So you can remove that and that will work just as well. And then we activate the AI unit in that case. And that's basically it. Though we have one last one here. This is called when a unit ends its turn. So this is called from, I believe, the player controller, or maybe, yeah, I think so, or the AI controller. If we choose next pawn, then we also delay for a little bit, perhaps set by whatever calls this event. And then we reset the current move of the current pawn to its max move. So the next turn it will still have its maximum move value, in case we are using movement where you can split up your movement. And then we set has acted this turn to true. And then we set the current pawn to be last in initiative order. Remember, this is when a unit ends its turn. So that means it is currently at the top of the initiative order, but now we want to move it at the bottom. So all other pawns get to act before it gets to act again. So then we use this function, which is let the first pawn in initiative order become the last. It's a bit biblical, but descriptive. So how do we do this? Well, we get the pawn at initiative order 0, that means the current pawn, and we set it to be at the index of the initiative order, which is equal to the length of the initiative order array. This means that it's one more than the maximum indexes in the array, and so we have to increase the size of the initiative order array by 1 to add this. So that means after doing this, we have an initiative order which has the current pawn on the top and at the bottom. So therefore we also remove index 0, the first index, and that's sorted. Okay. And then we find whatever pawn is currently at initiative order 0, that will be our next pawn, and we cast it to unit parent, and we set the current pawn to be equal to this new pawn. And then we again check which faction it is and do all the stuff we were talking about earlier. So that's basically the game mode. Actually, it's a bit simpler than the last one, the grid manager, I mean. Okay, so let's move on to the next. I mean, it's natural, I guess, to look at the player controller next, where we handle all of our input and a lot of other stuff too. So, okay, here are a few different things to look at. Let's start at the beginning. So also here we set up a few things. at the event begin play, and we just set up some references so we can easily reference these other actors later on. We get a reference to the grid manager, such the grid manager reference, and to game mode. So that's that. Okay, so activate unit. This is what is called from game mode that I was talking about earlier. So when we activate a player unit, what happens? First we set disable input here to false. We want to be able to have input after we activate a unit, and we set the idle value of this unit to true. This interacts with the unit's parent blueprint. And then we activate the pathfinding functions. Okay, this is one of the big ones. I'll have to speak about this one for a bit, I think, but you see that the pathfinding function has a lot of inputs. So firstly, it's called from the grid manager. It is within the grid manager, and it has a start index, which is let's see, which is the index that we start our pathfinding from, and it has a current move, which is the range in which we want to search for possible paths to move. And then we have continue beyond move range. This is, do we want to continue searching beyond what is the move range of the unit? And this can be used for a few different things. For AI, it's used to, if the AI doesn't find any enemy pawns within its movement range, then it continues searching until it finds one, and it moves towards that pawn. For players, you can use it to display some tiles as not reachable, but you can reach them in the next turn, as you would in Civilization, or have a different sort of color tiles for tiles that you can dash to, or you would have to add that yourself, but that would be quite simple. And then we have can you move diagonally? Is it possible to cross corners? Do we display the tiles? We usually want to do that for the player, not for the AI. And we have another one, AI stop continue if target found. We can activate this for the AI. So if we've set it to continue searching beyond the movement range, should we stop searching at the moment we've found a possible target? So this is can be useful to not have it search on for a very long time, which can be slow. So that's the inputs of pathfinding. So to show how it works, we'll try playing here, and it's perhaps easier to explain if I show a unit moving. So in this case we have the start index of the pathfinding function here, and it is out to the move range of this pawn, which is 6. And it depends, of course, on the terrain and on pawns that are in the way. So how does this pathfinding work? Well, it's using something called Dijkstra's algorithm to get this pathfinding, or something similar at least. So what we're doing basically is that first we start with this tile, and then we look at all of its neighbors. So we look at all of these tiles here, and then if there is nothing on them, if there's not another pawn on it, if it is walkable, if the edges between this tile and the edge on this tile are both not 0, and they are lower than the remaining movement of our current pawn, then we add it to an array, to an open list we call it. So this is one tile that we are going to search further. So we look at all these tiles. So it starts here. We can add this. The edge here is 1. Then we can add it. We do the same with all of these, and then it finds the edge here is 0, even though the edge here is 1. So we don't add this. And then when we've added all of these, it looks at one of these tiles, and then it looks on all of those that are around. Can we move to this? Yes, we can. This? Yes, we can. This? We can. Yes, we can. This? Yes, we can. But it has already been added to the open list, so we don't add this. And then we look at this tile, do the same thing. We do that over and over and over again until we have reached our movement limit. And then we display all of these tiles. Also, there's one more thing. Every time we add a tile, we also add a reference to its parent. So this tile knows that this is its parent, because this is the tile that searched for that tile first. And this will be the parent of this tile, for instance. So then, when we have an endpoint like this that the player is hovering over, we look at this tile and we see, what is the parent of this tile? Oh, it's this. What's the parent of this? This, this, this. And that way we can generate a path by looking at the parents of each tile. So that's basically how it works. And now we'll look at the blueprint so we can see that in more detail. Okay. So let's see, so we're going into the pathfinding function, which is contained within the grid manager, as you can see here. It's a pretty big function and there's a lot more hidden inside, but we'll take it one step at a time. So we start here with all our inputs. We set the start index to current index, move range to move range. Then we clear all in-range mesh markers. So if we had any of these blue markers there beforehand, we want to make sure that there are no meshes here. So we clear them all, and we clear them. If we're using decals, we clear the decals by doing a loop through our decal array and destroying all of them. Or if we're not using decals, we're clearing all the instances of these tiles in sight and tiles in move range instance static meshes. And then we set max move. This is how far we will want to search in total, which is equal to move range plus continue beyond move range if this is higher than 0. Then we clear the reachable pawns array. This is an array that keeps track of all the pawns it finds when it searches around our current pawn. So we clear that so we don't get any of the old pawns that were added in previous pathfinding searches. And then we clear the can move to array, which holds all the possible tiles we can move to. We don't want to keep any of those from earlier searches. And then we resize the can move to array to be the size of the grid again, because when you clear it, it's set to 0. Then if max move is higher than 0, if it isn't higher than 0, then we might as well not do the pathfinding, so we just stop. If it is higher than 0, then we continue. Then we add the index of the current pawn to the open list. So that means this is the first index that we're going to search for neighbors. And it has a cost of 0, and its parent is itself. Then we do a for loop. So we loop and we check movement and we search for tiles until we have reached our max move. So max move is the last index here. Okay, so we start with our first index. So that means we're checking the tiles that we can move to at movement of 1. And then we search and add adjacent tiles. So how do we do this? Well, we look at our open list, which in the beginning, remember, is only the only thing on the open list is the index of the current pawn. So we look at that, and then we want to look at all its neighbors. So we do a loop and we check, is max move lower? Is the array element cost? So that means the cost to move to whatever tile we are searching from now. So yeah, the cost of this tile would be 0. The cost to move to this tile is 1. The cost to move to this tile is 2, and so on. So if we're looking at this, this has a movement cost of 2. So we look at the tiles surrounding it. But before we do that, we want to know, is the cost to move here lower than the maximum move of this guy? If it isn't lower, if it is as high as the maximum move, it's no point searching, because we can't move to any further tiles anyway. So we check that first. If it is true, then we check if the array element cost, same thing, is equal to the current search step. now the current search step, it will start at 1 because this is the first. We search for movement number 1, and then we search for movement number 2, and so on. So if it is higher than current search step, that means that it probably has a higher cost, like one of these slow tiles here. So we wait, we don't search for that yet. We wait until the current search step is equal to the cost of moving to this, or moving from, actually in this case, that tile. Yeah. So if we don't want to look at this yet because the cost of moving from it is too high, then we add it to the delayed search list to be searched later. If it is true, we want to search it now. So we check if it's a hex grid or not, and we have some different kinds of searches if it's a hex grid or not a hex grid. So we'll look at square grids first because they're easier. So here we search north, east, south, and west first in the square grid. So here we are. So this is east, west, south, north, as I've explained before how these work. So this is like, the index to the right, because it's +1, so it's one array index higher. And for this we want to search this tile and add it if we should add it. So the direction we are searching, so this is the index we are searching, which is equal to the index of the parent plus 1, so the one to the right. The index of the parent is simply that, the index of the tile we are searching from. Parent cost is the cost to move to the parent, and then we look at the edge of the child. That means the new tile we are searching at. What is the value of its edge? So if it's 0, we don't want to move to it, for instance, because that indicates a wall. And the edge of the parent, the tile we're moving from. If the edge towards the tile we're moving to is 0, we don't want to move there either. So, search and add tile. Firstly, we check if the tile we are searching now is already in the can move to array. That means it has already been searched. In that case, we don't want to search it again, or we'll have an infinite loop. So we stop there. If it's true, if it's not on the list, then we check, is the edge of the child, is it greater than 0? And if it is, then we may want to add it. And then we check, is the edge of the parent greater than 0? If it is, then we might want to add it. And then we check the pawn array of the index we are searching now. So is there a pawn on the index? So if it's not, if it's empty, we may want to add it. If there's a player on it, then we add it to the reachable pawns array. This is used by the AI to find a target. If there's an enemy on it, let's see now, we're saving again. Yeah, if there's an enemy on it, we don't do that. So, if it's empty, then we check, is the cost of the parent, so the cost to move to the parent we are searching from, plus the edge cost, the edge cost of the child we're moving to. So we add those together, and is that lower or equal to the maximum move? If it is, then that means we can move to this tile, and we add it to the open list, so it can be searched later. That we search for new parents, new children, I mean, for that tile. And then in that case, and also in the case if there's an enemy or a player on it, we add it to the can move to array. So it means that we can move to this tile, we can move to these pawns too, but we can't move from those tiles that there's an enemy or player on. So we don't want to search with that tile as a parent. So you can modify this if you want to be able to move through friendly pawns, for instance, though that's not how it's set up by default. And yeah, that's basically how the pathfinding works, though there's a bit more to it. still. So then we check, do we want to search diagonals as well, which is depending on the diagonal movement boolean here. So if it's true, then we search diagonals just like we would search northeast, south and west, basically, because there's no difference. If we cannot cross corners, then we have a slightly different and a bit more complicated version, because this one, in addition to checking the tile we are moving from and the tile we're moving to, if we're moving diagonally, we also have to check the edges of the indexes that are between the two tiles we are moving between. So we also get some of these other tiles, and we also check these. So we check 4 different tiles to see if their edges are higher than 0. But other than that, it's basically the same. So for hexagonal tiles, you never have to worry about corner crossing because there's no corners with hex grids. But you do have to worry about whether you're on an even or an odd row, because that's a bit different from each other. I can explain quickly why, actually. So, thing is, if I should make a small grid for this so it's simpler, or I can just make this grid smaller temporarily, or a bit larger. So, there. So this is one of the even grids. So if we are here on number, so this is 0, 1, 2, and we want to search all of these. So we want to search the one that's +1, the one that's -1, and we want to search the one that's +1, 2, 3, 4, right? And so the one that's +4 and the one that's +5. But when we're searching our odd rows, like this row here, we want to search +1, -1, just like before, but we want to search 1, 2, 3, 4, 5 and 6, right? Instead of 4 and 5, like it was before. So we have to make these small adjustments for what row we are on. So we check which row we are on by doing some simple math, and then we have 2 different, slightly different functions, which are basically the same as the last one we went to, but we're checking slightly different indexes each time. So that's the basics of how that works. And when we have searched and add tiles, we clear the open list. We don't want to search the same tiles again. We add one to the current search step. Maybe we want to display the tiles. That's depending on this boolean, which is connected to the start here. So if we want to display them, then we check, is the move range lower or equal to the current search step? So are we searching now beyond the move range of the current pawn? Then we might want to display a different kind of tile. So I made a couple of different functions here. So if we are still inside the movement range of the pawn, then we want to add a tile in move range marker, so either a decal or a static mesh. So if we're using static meshes, then we check in the open list children. So this was, like you seen before, we added all the new potential tiles to move to the open list children in the earlier function, and for each of them we want to add an instance of the tile in move range material component at the rotation of the rotator array, and at the location of the vector field array on the index of that particular tile. And we have it hovering above the grid slightly, so it's not overlapping completely the grid by a very small amount, which can be set customly, or can be customized in the grid manager. For decals, it's pretty similar. We get the same indexes from the open list children and let them through the vector field array to get the location, and we spawn a decal now it's difficult to delete all the decals later, or to find a lot of decals and delete them. So we make sure to add every decal we spawn to an array, so we can easily find all of them, and so we can delete all of them at once later when we want to do that, like you saw in the clear tile in range marker meshes function we looked at earlier. So that's that. And this one at the edge and beyond is similar, though with different meshes. Okay, then we want to stop pathfinding if there are no more tiles to search. So if the open list children is equal to 0, we don't want to continue to search even though we still have more movement to search for. Could happen, for instance, if you're blocked in by walls. We don't want to continue searching. So if there's no possible new tiles to search, we stop searching. But if there are any someone to search, we have to check, is the current search step lower than the move range of the current pawn? And if it is, then of course we want to continue searching. If it is not, then we check, is it lower than the maximum move we want to search, if we want to search beyond the movement range of the current pawn. So if it's not, we stop. So if it is, then we want to check, should pathfinding end if a unit has been found? So it should not stop, then we just continue until we've reached our max move. And should we continue to search if no targets have been found? This one. So yeah, that's what I was. Yeah, so these are connected in that. So it's checking the reachable pawns array. So if it has found a pawn, so it's not equal to 0, then it stops. If it has not, then it continues searching. So if it continues searching, it appends the open list children to the open list. That means all the potential tiles, we now make them actual tiles we want to keep on searching. And we add the delayed search list, the one we saved that we could not move to yet. We also add that to the open list so we can search them again. Maybe we can move to them this time. And then we clear the delayed list and clear the open list children. And here's some junk I've kept, it seems. Okay. So if we end the pathfinding, then we clear the open list children in this case as well. We set the current search step to 0, so next time we run this, it starts at 0. We clear the delayed search list in this case as well. And we add the index, the current index, that means the index we started searching from, we add that to the array of tiles that can be moved to as well. And that's the pathfinding in quickly described. I hope it makes sense. Just look into it more yourself, and hopefully it will make even more sense. And if you have trouble understanding it or want to modify it, just send me a message. This is kind of the heart of the toolkit in many ways. But we were talking about the player controller, weren't we? So we call that when we activate a unit, but we also call the find tiles in range. So we simultaneously try to find all places we can move to and all tiles we can attack, basically. So this is also one of the really big functions, and also within the grid manager, contained within the grid manager. So we have a few inputs here. Start index, just like in pathfinding, this is the index we search from. Range, this is how far we want to search. Check visibility, this is do we want to check if there's anything blocking in between. So I should probably just make a new stage to make this easier. Let's see. And I like to have it zeroed out, even though I've added a lot of stuff to make sure that's not a problem. I still prefer it. And there, and some tiles. There. And let's make sure this guy has some... Oh yeah, you can't, of course, see his visibility, or can you? let's see. Yeah. So now this is visibility. So in this case, we're checking visibility to the tiles. So these tiles are obviously in the range from his range of 6, but you can't see them because there's a tile in between. So this is what we're checking here. Yeah. And do we want to only find pawns? That means, do we only check tiles for visibility where there are pawns on them? So let's see, if we add an enemy and we set this to true, let's see, like this, then only the one with the enemy pawn should light up. Yeah, so as you can see here, so it lights up, and that's actually how it is by default now. So if we have no movement left, then we check to all tiles so we can display our entire movement or our entire visibility. Now if we are checking movement at the same time, we only check the tiles which have pawns on them. So you can see that it's like that by default, and I did that because that's pretty quick to calculate anyway. If you only want to check the tiles with pawns on them, it's very quickly done, so you can do it simultaneously when you do the pathfinding. It's different from some of the older versions. And which factions are we searching for? So in the player case, we're searching for enemies. And do we want to display the tiles? Do we want to have a diamond-shaped searching? So let's see, kind of self-explanatory, I guess, but it's so slow to start up today. Yeah, so it's in diamond shape. There, and we have a max Z difference. That means if we're using height maps, so that some pawns are a lot higher than other pawns, what is the maximum difference we want to be able to search between the current pawn and the target? So this is to prevent someone who has like an attack range of 1 from attacking someone who's standing on a ledge, like way up above him, but on the next tile. And this is by default set to be a function of dependence on the range of the current pawn, and a minimum range. We can also set that. So let's see. Yeah, so in this case there's a minimum range where you won't have visibility to, so I know that this is used in some games. Right, but how does this work? Find tiles in range. So this is also one of the big important functions, and it can be used for many other things than visibility. For instance, it can be used for an explosion effect, where you set the center of the explosion as the start index and the range is the radius of the explosion, and then you can find all the pawns that are on the indexes that you find, and then you can deal damage to them, for instance. So it can be used for a lot of things, and it's and it is quite a bit different from pathfinding. And I mean, what may seem like makes the most sense is why not just use the pathfinding to find whatever is in range. That's because it's well, it's pretty fast, but it could be even faster when we don't have to care about obstacles or anything. We can make use of some tricks that will make searching a lot faster. This is what I've done. So a few functions are contained here. So first we get indexes in range. This is simply that we find all indexes that are within a certain range of the pawn. We don't care about anything else, firstly. And yeah, so it's also one of the big functions, but there's a lot of stuff that's repeated here. So like in the pathfinding, we set a couple of values depending on the inputs, so we can reference these easier later. And then we set a few values that are called range check west, range check east, and so on. So if a pawn is standing like this, like in the middle of the map, these will all be equal to his range. So all of these values will be equal to 6. However, if he's standing like this, so he's standing close to this wall, which is, let's see, the north wall, then his range check north will be 2. That means he's only 2 tiles from the top. So this is to tell the function to not search any tiles beyond the top here, which wouldn't make sense. So we set all of these values, we check, we do that by doing some simple math to check how far is the pawn, or the current, or the start index in this case, from the different edges, and we set all these values. And then we start searching for tiles. So let's start with the simple one again. So we, without a hex grid and not a diamond shape, that's the simplest of all, we're searching a square around the pawn. And how do we do this? Well, we first add all tiles from north to south. So this means that we take minus range check north all the way to range check south. This means in this case, or let's take a smaller range. In this case, we're looking at the tiles that are 3 up from in, 3 north, and all the way down to 3 south. And for each of these, we want to check all tiles, or 6 tiles, for every step. And to do this, we have a nested loop, so we have another for loop that goes from negative range check west to positive range check east. This is a bit tricky to explain, I guess, but that's basically what I do to find all those indexes, and you just have to look through this and make sense of it. This one isn't too hard, and then the other ones are a bit more tricky. Actually, I've done this through quite a bit of trial and error, so it would actually be quite difficult to explain without spending ages on it and thinking quite a bit through it myself. So hopefully this makes sense for you. I'll help you out if you're having any problems with it. But in any case, for all of these tiles, we want to add them to the tiles in range array. So we add each of their indexes to the array, and we also add the distance that each of these indexes are from the start point, which we find by taking the maximum value of the absolute value of each of these loops. Because if we're searching tile number, or we're searching on the loop number -2, for instance, that means it's 2 above us, right? And we're searching east +3, that means that we're searching like -2 + 3, we're searching for this tile. So this tile is, of course, a range of 3, right? From this guy, 1, 2, 3. So we just take the maximum value of these two. That will be the range if we're searching like in a square. And for hexagons and the diamond shapes, it is the same basically, though there are some more stuff added in to make sure that it keeps its shape even though you're moving close to an edge. But yeah, it would take some time to explain that, so and I'm not sure I would do a very good job of doing it either. So just look it through, and I hope you'll understand it if you need to understand it. If you need that for your game, then I'll help you out, like I've said, if you have trouble understanding it. Okay, that's one part of the find tiles in range. So now that we've found all of these tiles, then we clear some arrays that we're going to check in the next step. So we first clear all the tile inside range static meshes, instant static meshes, and we clear the range array, which we're going to use later. So we want this to be empty, but we resize it to the size of the map, and we also clear the pawns in sight array, so we don't keep that from earlier searches. When we've done that, then we check, will obstacles block visibility? If they do, then we run this one, find visible pawns. If it does not, then we do this other function instead that doesn't check visibility, which is quicker. So we can start with that because it's a simpler version of this, basically. We also, for this, we set, do we want to display the tiles? Do we want to, what is the faction we want to search for? Do we only want to find pawns? And all these are, of course, inputs from the original function. So in this case, we get the tiles in range array, which we added in the last step, remember? And for each of those, we check, are we trying to only find pawns here? If we are, then we only want to search this if there is a pawn on it with the appropriate faction. If not, then we want to search everything, so we just search anyway. And then we set the array element of the range array to the range. Oh, this doesn't look good now. But yeah, this should say distance. It says distance here at least. So the range array, we want to save all the distances. The range array is the size of the grid, and it is there so you can simply check by hovering over or clicking a tile, check the range array, how far away is this tile from the current pawn. So we add it to the range array, and we add it to the pawns in sight array as well. So actually the name here is misleading. I mean, if you're checking every tile and not only pawns, then all of the tiles will be added in the pawns in sight array. So it could be maybe named targets in sight array, really. After we've done that, we want to know if we display tiles or not. If not, then we're fine with just adding it to the arrays. And if we do, then again we check if we want to use decals. If we're using decals, we want to spawn a decal at the appropriate location and also add it to the current decals array. And we're getting the location by getting the index that we're searching at the moment and having it go through the vector field array. And in case we're not using decals, we're adding an tiles in sight range static mesh instance instead. Okay, but what if we want to only find visible pawns or visible tiles, really? Then we do much of the same thing, really. All of this is the same, but this is the biggest change, that we also do a line trace between the index of the current pawn, the index we started searching from, and the index that we're wondering if we have visibility to. And if nothing is hit in between, if nothing blocks range trace, in other words, if the return value of the trace, the range trace is false, then we want to add it. If not, we don't, because it's blocked. And also we want to check the difference in height between the two different tiles, or the index that we start at and the end index we want to search. And we compare this to, let's see, we compare this to the maximum Z difference, or yeah, the maximum Z difference here, maximum height difference, in other words. So if it's the difference is too high between, too large between them, then we also don't want to add it to the range array or the pawns in sight array. Other than that, this is exactly the same as the previous function. Alright, so let's look at the player controller some more. So this video is turning out to be quite a bit longer than even I anticipated, so I hope you haven't fallen asleep yet, though I applaud you if you made it this far. Yeah, like I said, I'm going to add some links below to whatever parts you find relevant, so you don't have to watch the whole thing. But yeah, it will be useful as a reference, hopefully. I spent a lot of time on it in any case. But yeah, so now we have found the tiles in range, and then we set the visibility of the hover marker. So if it has been invisible before, then we set it to be visible now, so you can see which tiles you are hovering over. And that's how that works. So now, after we have done this, that means that we have a can move to array that is filled up, and we also have some tiles in range arrays that are filled up, like the range array. So later now we can check when we click a tile, is this tile in the array that we can move to, is it in the array that we can see, and we can decide what we want to do with that information when we click. So let's look at that. Choose action depending on tile clicked. So this is the input action click. So this is an input action which is contained in the input in the project settings here, where we have the action mappings of the mouse wheel and clicking, as well as the panning and rotation of the camera. So when we click, we want to check, is this the player turn? If not, we don't want to do anything. If it is the player turn, then we check, is the input disabled, which it would be if we're moving, if the pawn is currently moving. So if it is not disabled, then we want to check, okay, let's get the tile that is under the mouse, and see what kind of tile it is. So we use this function, which is also in the grid manager, get hit tile location and index. Now, how does this work? Well, it gets the player controller and gets the hit result under the cursor, just like you would in any click action in any sort of Unreal game, and then we break the hit result, we get the location, and then we run this, we output the raw location itself, but we also output the index, and then we use this vector to index macro, which is here. So this converts the location hit into an index, and this also has two different versions, one for a square grid and one for a hex grid. And I don't think I will delve into this in much detail, but basically it gets the size of the different tiles, and so it divides up the location you hit by the size of the tiles, and then converts that into an index. And it's a bit more complicated on hex grids, because you have to take the offset of the odd and even rows into account, and also that the distance in the y direction is smaller than in the x dimension. But yeah, so it outputs a single index value, which is used later. So now we have an index, we only use the index here, and so we set this to the clicked tile, and we only do it if our trace is a hit. So this is a trace, by the way. The trace is with the path trace. So if we click something and it does not block the path trace channel, then we don't do anything. But if it is, then we set click tile to that index, and then we check the tile that we have clicked. Okay, what is on this tile? So we check the pawn array on that particular index, and we check, is it empty, is it a player, is it an enemy? So first, let's see what happens if it is empty. That means, if we click an empty tile, we want to move to it if we can move to it. But if it's outside the move range, we don't want to move to it. That's what we want to do, and that's what all of this is. So it's empty. First we said target is pawn. The target we click is not the pawn, right? And then we check, is the tile we clicked within move distance? So does it have a cost in the can move to array? Now all of these looks really weird now, but yeah, you can see here, index cost parent. So if the cost of moving to this is greater than 0, that means that it's possible to reach it. It was added to the can move to array. So that is true, but it also has to be true that the tile we have clicked, or that it's lower or equal to the current move of this pawn. So if both of these are true, then we want to move to it. If they're not, then we check okay. But it's still, we can still move to it. It is within the can move to array, but it's beyond the move range of our current pawn. This is if we have searched beyond the move range of the pawn. So we might want to do something different then. In this case, let's see. So if it is still, so if that is true, it's still in the array, but it's outside of the range. Then we also set target is pawn to false. Why do we do that exactly? I think that might be redundant. Yeah, because of some other stuff here. Yeah, so we set that. That's for a different reason. So if it is outside the move range, which we now know it is, then we get the closest tile to the target instead. And we do that by using this function, which is the reachable index closest to target. This uses the path index array, so we haven't touched on that yet. So yeah, I'll have to get back to this actually. But yeah, so in any case, we find whatever index is closest to the index we have clicked, and we move to that tile instead. So we set that, whichever tile is closest, to be our new, the new target click tile, even though we didn't really click it. I can show how that works actually. So let's just change up this guy's move, and let's make him move beyond the move range, like this. Let's see. Yeah, oh yeah, we're still using the hex tiles here. But here you can still see the path to all of these, but you shouldn't be able to move to them. So if we're clicking one of these, you see we'll find this tile instead, I think. Yeah, so he finds the closest one instead. That's how that works. Okay. So we set that to be the click tile, and then we run all the movement stuff. Now, if it is not, if it is not within the can move to array either, then we want to just say nothing happens. So we set target is pawn to false. We set disable input to false, so we can click something else because this didn't do anything obviously. Yeah, if the current move of the current pawn is 0 and we click any tile where nothing happens, we want to end the unit turn. You could do this like with an end turn button instead, but that's how I've made it work. So you can see that here. So this is simply that when we have moved all our movement, can't move anymore, we only have the tiles inside range, and we click any empty tile, then our turn ends. So that's what this is. Okay. But if we have clicked a tile and we can move to that tile, or if we couldn't, but now we found a new tile we can move to, then we set disable input to true. We don't want to be able to click any new tiles and confuse all the pathfinding stuff after we've clicked and have found a tile to move to. So we set the marker location of the target marker, the marker that shows which tile you're moving towards. We set that to be the location of the click tile by using this set marker location function. This is one of the uglier ones. I should spread this out a bit. But yeah, so here you can set either a decal or a static mesh, so it's a bit different depending on each of these. But basically what it does is it runs the index that you're interested in through a vector field array, or through the index to vector on grid function, and then sets the location of the decal or the static mesh to that location. Or if you've inputted a location instead, and you've set use index to false, you just use that location. But you also run it through some of these arrays. Yeah. Okay. So when we've set the location of the marker, we set its visibility to true, so we can see it. And we check, is the target pawn? That's the thing we checked earlier, right? Which is false in all the cases we've seen so far. In which case the click tile the target index will be the same as the click tile. That's the tile we want to move to. And then when we have found the target we want to move to, we want to find the path within that pathfinding array. So that means we want to look in the can move to array, we want to look at the index of the target, we want to look at the parent of that index, find the parent of that index, and so on until we get back to the start index, and then we draw a spline or whatever we want between those tiles. So that's what we do with this, which is one of the other big functions within the grid manager. So here's what we do. We also have a few inputs, the path end, of course. We don't have the path start because that will always be the start of whatever last generated the can move to array. Then we have some inputs. Do we want to create the spline? The spline is of course used for displaying the movement path and also moving the pawn along that spline. Do we want to display the path? And if we want to display it, do we want to display it as a spline, or instead, if false, we will display it as instant static meshes, the arrows that I've shown before. So we start by finding the path from the index. So we find it from the end index until whatever first generated the can move to array. So first we clear the path index array, so make sure nothing overlaps or we don't use any of the old stuff, and we set the path holder temp, the temporary variable, to the end index. And then we add the temporary index to the path index array. So this is the first index of our path, is the target we want to move to. And then we get that index and we check the can move to array, and then we get the parent of that index, and then we make that parent the new path holder temp, the new temporary variable. And then we check, okay, now we've done that. That is the cost of that tile equal to 0. If it is, that means we have reached the start point, because that has the cost of 0. If it does not have a cost of 0, then we do the same thing again. We check the path holder temporary, which is now the parent of the last temporary, and then we add that, and we check the cost of, or we check the parent of that index, and we check the cost of that. And so on until we have found the first generating index. And after that we have an array that contains the indexes of each of the points of the path. And then we clear the path vector array. Let's see, why do we do that? Oh, I can't remember, I hope it's not important. Maybe it's some old functionality. I'll have to look into that. In any case, let's see. It's always so difficult to go back to whatever it was in before you enter the function. I'll go here. So then we check, do we want to create a spline? If not, we are happy with just having the path index array. This is what we use for most stuff anyway. But do we want to create a spline path? If yes, then we create a spline path. So then we get all the indexes in the path index array, and for each of them we make a path vector array. I should probably clear the path vector array here instead of the old function. But we also add the spline height, and we get each vector and we have it go through the index to vector on grid function, so that we get locations instead of indexes. So we can create, because we need to have vector locations to create a spline, right? And we have the height of that spline. Yeah. Okay, so here we have an array that is basically identical to the path index array, just instead of indexes we have locations. and this shouldn't be connected actually. I have to remove that. That doesn't matter in 4.7, but in 4.8 and onwards that makes a difference. So that shouldn't be there in later updates. Okay, so when this is completed, we add the current pawns index to the spline path as well, because the current pawns index is not part of the path index array. So we need to add that manually. So we're getting the current index and we're adding it to the path vector array. And then we set the spline world points. This is a function that comes with Unreal, of the path spline. So we set all the points of the spline to be the points that we have in our path vector array. So now we have created a spline, and we have some outputs, just in case you'll need that. I'm not using it though, but it's useful at a glance to see what is made within this spline path. Okay, then we check, do we want to display this path? If not, then we just stop here. We have our spline, it's invisible, but we're not going to display it. If we want to display it, do we want to display it as a spline or as instant static meshes? If we want to display it as a spline, we do it like this. Yeah, this is not my strong suit, but in any case, we start here by destroying and clearing the spline path. So we get all, we have this spline mesh array, which contains all the spline meshes from our previous spline, if we already had a displayed spline. And for each of these, we destroy the component, and then we clear the array. Yeah. So after we've done that, then we have a for loop that runs for as many loops as the length of our spline divided by let's see, divided by the length of our spline mesh. And the length of the spline mesh, if you remember, was set in our grid manager to be dependent on the size of our default tile meshes. But yeah, so we run a loop, and for each and through this loop, what we want to do really is to add a lot of spline mesh components that constitute the entire spline. So the spline is like invisible, just based on math, but it contains a lot of small segments, small meshes that are bent along the spline. So we want to add all of those small mesh components, basically. So we do that a number of times, yeah, like I said, depending on the size of the spline and the size of the spline mesh. And for each of these loops, we add the spline component, a spline mesh component, and we set its static mesh to be the spline path mesh, which is set in the public variables. Then we set its material to be white emissive, which is the default I've chosen. And then we add that component to the spline mesh array, so it can later be deleted in this function. And then we set the start and end points of that particular spline segment. Yeah, which we do by getting each of these segments, where we take the index and we multiply it by the spline mesh length. So for index 0 we get the first segment, for index 1 we get the one that's the distance of one spline mesh from the beginning, and so on. So we get all these little components. And for each of them we get their world location and distance along the spline, to generate the spline itself. It's been a while since I made this, so that's how well I can describe it, I think, but that's basically how it works. Okay, and if we want to display it as instant static meshes instead, and it's a bit simpler, we clear all the path meshes, which are the little arrows, and then for each loop in the path vector array we spawn one of these little path meshes. And yeah, the location Z, that should be changeable from outside. Yeah, well, I'll change that later. And we set the rotation to point to the last point of of the path vector array. So we get the path vector array, and we find the one that's before the one we're spawning a mesh for now, and then we're finding the look at rotation between whatever mesh we are currently placing and the mesh we placed last. So that's how that works. Okay, I think that's the entire find path within pathfinding array function. It's also an important function. After we've found that path, then we set has acted this turn to this pawn to be true. This is to make so that after he has acted, if we can split up the move so he can move a bit and then move some more, that we can't, if we are able to switch to another pawn, we are not allowed to do that after he has moved a bit. And yeah, it's also used for some other stuff. After that, we just to make sure and then we clear all the in-range mesh markers, and we destroy and clear the spline path so that all these little blue meshes and the spline path doesn't remain after we or when the pawn is moving. It looks better that way, I think. Okay, and then we set the array element of the current pawn, which we get from the game mode, and we find the index, and in the pawn array we make that index empty, because now that pawn has left that index, so there should not be a pawn in it anymore. And we do the same thing for the pawn actor array. In this case we set the array element to nothing. There is no pawn contained on that index anymore because the pawn has left. And then we begin the movement of that particular pawn, which is called, let's see, because that's continued in the event graph of unit parent. So target is unit parent, so we'll go to that later. That's the physical movement itself. And then we set the visibility of the hover marker to be false, because we don't want to show that while we're moving, or that's how I prefer it in a way. And we check, can our pawn split up move? That means when we have moved part of its movement, will we allow it to move, be able to move more afterwards? So if it can split up move, we set the current move of this pawn to be equal to whatever was its current move before, minus the cost of moving to its new target. Now if we don't want it to be able to move afterwards, then we just set its current move to 0. It's used up. And in the end we also clear up the can move to array. Might be unnecessary because we do that in the pathfinding, but I do it just to be sure. Okay, there was some more stuff here I didn't go to. So if the target is pawn, yeah, that hasn't happened yet. So let's first go to this. We click something and it's not empty. It's actually an enemy. So what we do then, a lot of different things can happen in that case. So is the target within attack range? This means when we check the range array that we generated in the find tiles in range function, if you remember, if this is higher than 0, that means that it does have a range to that tile, and that we can attack it directly from where we're standing. So if it does, then we disable input, we clear all our meshes and the spline path, and then we attack victim, which is also a function within the unit parent, so we'll look at that later. And then we make sure it's not idle anymore because it's attacking. But if it is not within our range, then we set target is pawn, because maybe we can move to and attack that pawn even though we can't reach it at the moment. So we set target is pawn, and then we do our whole checking here. Okay, can we move to it and all of that. So now we can move to it, and yeah, if we click an enemy and it is outside our move range, then we can set target is pawn to false, because we're going to move to the closest tile, right? So the target is not pawn. But if we can move to it, as found out by this branch, then we do much the same as we did before, but now target is pawn is true, right? So we don't want to move to the target we have clicked, because then we would be standing on the same tile as a target. So we want to be standing at at the tile in front of our target instead. So then we check if we clicked this pawn, is it adjacent to us? So if it is, we don't want to start moving towards it. This is just a safety feature, really. It should never fire through. And then we get the path index array, and we get index number 1. So remember, index number 0 was the target. So index number 1 is the index or tile in front of that target. So we set that to our target index and move towards that instead. So that's that. Okay, so that's both of these. Now, to end it, if we are clicking a tile and there's a player pawn on it, what do we do then? Well, that depends really. So it's a player on it, and is the index of this tile the same as the current pawn's index? This means that we have clicked the current pawn. So if we click the current pawn, what do we do then? Well, the way I've designed it is that if the current move of our current pawn is greater than 0, then we want to set its current move to 0 and activate it. This means that it stays where it is, and then it checks for tiles in range. So just to show that. See. Yeah, so we click ourselves and we find the tiles in range. So there you see it in action. Now if the current move is not greater than 0, that means we have already moved probably, then we just end our turn. So you can also see that here. See. So we click ourselves first thing, and now we have no movement, and when we click ourselves we end our turn. So I've designed this to be, without any sort of buttons for ending unit turn and stuff like that, which are often in these kinds of games, to make it as like simple and stripped down as possible. But so that's sort of an intuitive way to do that, I think. But it's easy enough to add other interface buttons instead. So, but yeah, if this is false, that means we have clicked an index which has a player on it, but it's not the current pawn, so we've clicked a different pawn. So can the player switch pawns, which is set in the grid manager? If it can't, then we don't bother doing anything. You can click that pawn all you want, nothing's going to happen. But if we can switch pawns, then we check. So the pawn that we are clicking, the click tile, finding the pawn actor array, getting that pawn in particular, we get his has he acted this turn variable. So if he has acted this turn, then we don't want to be able to switch to this guy because he has already acted. If he has not, then we want to be able to switch to him. And then we find our own pawn has our own pawn acted this turn. So if he has acted already, so we have, let's say we have moved a bit, or we have moved but we haven't attacked yet, and then we switch, we don't want to be able to switch back to him. That's how I made it in any case. Though if we have not done anything yet with him, we want to be able to switch back to him later. So we get a few different things happening depending on that. So if he has acted this turn already, we want to let the first pawn in initiative become the last. So the current pawn, we move him to the back. I've talked about this function before in the game mode. So we run that, which is from the game mode. And then we set the current move of the current pawn to be equal to his max move. So that next time he's selected, he can move his max move again. But if it is not acted this turn, like I said, then we instead just set the unit that we have clicked to be the first in initiative. So the unit we have clicked is moved to the top, and the pawn that was, or the unit that was the current unit, is now the next in line. So after he is done, we will go straight back to the previous pawn we had selected. Then again we clear all the in-range mesh markers, and we set the current pawn to the new pawn that we found on our click tile, and we activate that unit. So this thing actually bypasses all of the game mode stuff and does it on its own. I've considered moving this over to the game mode instead, since it perhaps makes a bit more sense there, but I've kept it here for now. And then we set is panning to false. This is also similar to what we do in the game mode. Yeah, so that's all of the different things that can happen when you click a tile. So there's one more thing left in the player controller, and that's the display path on hover. So when we hover over a tile, we want to display the path to that tile, right? And there's a couple of other things here as well. That every tick, when we hover, we set the marker location of the current pawn to be equal, or the marker location of the current pawn marker to be equal to the location of the current pawn. So that's, let's see, easier to visualize if I show how it works. That's this mesh here. So that's always on the current pawn. So it stays with us, and when we change to a different pawn, you can see now it's around this guy instead. So this is, uses the set marker location function to do that. And then, after we've done that, we get the tile location and index, the index under our mouse. I've also talked about this function before. And we set the index to be, we check first to see, are we hitting the path trace? Is this a tile that can be moved to? So, if it is not, all we want to do is delete the old path. But not display a new one, because we can't move to that path. But if we did hit, then we check, is the tile we hit different from the last tile we were hovering over? If it is not, we don't want to generate a path again, then we generate a path every tick, which is completely unnecessary. So we only want to generate a new path if we are hovering over a new tile that is different from the one we hovered over. But if it is different, then we set that to the new current tile hover. And then we set the marker location of the hover marker to be equal to the location of current tile hover using this function. And if it's the player turn, we also want to display a spline, or a path in the case. So we check if the current pawn is idle, so if we're moving or attacking, we don't want to show these sorts of splines. But if we are idle, then we check the tile we are hovering over. Is it empty? Is it a player? Is it an enemy? If it's empty, then we want to display a path, right? But first we check, is the can move to array, is the cost higher than 0, just like we did before. So if it is, or greater than 1 actually, let's see, does this work again? Yeah, greater than 0. And we find a path within the pathfinding array, the function I described earlier, and create a path spline display path, and so on. So if it's not greater than 0, that means we can't move to it, we just want to destroy it, the old path. By the way, here you can see just the two different destroy functions, depending on where displaying is as a spline or not. So that's if it's empty. Now if it's a player instead, so if we're hovering over another player, we don't want to display a spline at all, so we just destroy it. If it's an enemy, then we check, is the range array larger than 1? I mean, if it's standing right next to, so this is whether or not we want to display like the straight line that we show when we're aiming over an enemy. So is it greater than 1? If it is 1, then we're adjacent to them, so it doesn't look good with it, just a tiny little spline like that. But if it's greater than 1, then we want to show that line. So in that case, we display a straight spline between points. If not, then we find, so if he's not within the range array, so we can't attack him from where we're standing, but we can move to him, then we want to display a path to that pawn instead, unless he's standing straight next to us. Yeah, so but if he is within range but outside range 1, then we display a straight spline between these points. So we destroy the spline path again, and we find a ranged attack path, So yeah, we clear a couple of or the path vector array here, and then we just have two different points in the path vector array. We have the target and we have the attacker, the index of each and the height of each. So we create two different points in our path vector array, and set the spline world points of the path spline to be these two locations. And then we simply display that path as a spline. Yeah, okay, so that's the entire player controller. So yeah, let's move on to the next one, shall we? I guess a lot of YouTubers split up their videos, and I guess there are some good reasons for that, but yeah, screw tradition, we just keep going on until I faint. So, what's next? Let's see. I guess the AI controller is up. It's kind of similar to the player controllers in a few ways, so should go fairly quickly, I hope. So here's the AI controller. So yeah, we also have an event begin play on this one that sets up a few references. I mean, like the grid manager reference and the game mode reference, just for ease of access. So when we activate the AI unit, you can see that this is pretty similar to when we activate a player unit. Even though we don't display the tiles, we continue searching beyond its move range, and we stop searching if a target has been found. So the inputs are a bit different. And when finding tiles in range, we also don't display them. We only find pawns to make it quicker. There's no point in finding every possible tile for if we don't want to display them. So we only find whatever is relevant to find. So that's pretty much the same. Then we append the reachable pawns array. If you remember, this is generated in the pathfinding array, all the pawns that we can reach, and the pawns in sight array, which is all the pawns we found that were visible with the find tiles in range. So we append both of these into the reachable pawns array. So now we know all our possible targets, all the possible players that we can attack. So let's check now. So now we check this new array. Is it larger than 0? So are there, when we searched our entire movement range and we kept going like for ages, and we tried to search visually and we still didn't find anything, then we just choose the next pawn. We don't bother. But if it's true, so if there is someone we can attack either in sight or in movement range, then we get all these reachable pawns, and we try to find the best one. We make a choice array between all of these possible pawns. Again, this shouldn't be connected. This won't work in 4.8. So we clear the old choice array, and then we get all the pawns in the pawn index array, and for each of them we add their current health to the choice array. This is how the AI decides who to attack now. It attacks whoever has the lowest health, really. So first it adds the health of all these pawns to the choice array. So that's easy enough. Let's see. So after doing that, then it finds the pawn with the lowest health in the choice array, and it does this by getting the choice array and finding the minimum of that float array, so that whoever has the lowest health float, and then it finds that index, and that index will correspond to the index in the reachable pawns array, since we use the reachable pawns array to generate the choice array. So then we have the index of the pawn we want to move to, and we get and we find that particular pawn, and we get that pawn's index, and we output that here. So with that output in mind, then we check inside the pawns in sight array to find, is this pawn that has the lowest health, is it within the pawns in sight array? And if it's let's see, so if it's -1, that means it returns false, we have not found it. So this way we decide, is the best target pawn in attack range, or do we have to move to him? So if it is within attack range, then we want to just attack him straight away. We just stand where we are and we attack them. So then we get the pawn with the lowest health from the choice array, same guy as we found here. We set that to the target index. So this is our target. And then we simply run the attack victim function on the current pawn. And which victim do we attack? Well, we attack the target, which is on this index here. Now, if the target is not in sight, so we have to move to him, then we also set the target index to this. This could be set beforehand actually, and would save some room. Yeah, I should do that later. But yeah, then we find the path from the index, from the target we want to move to, and we find the path to the current pawn, which is outputted in the path index array. And then is this target outside the pawn's move range? So we do that by checking the current move of our current pawn, and if that movement is lower than the length of the path index array, the length of the path we have found, then we just have to move to the closest one. So let's see. So let's first see. No, it's not outside. It is within range. So if it is, then the target is pawn, which you may remember from the player. And is it more than one tile away? So if it's not more than one tile away, then we don't bother moving and we just attack him, because we're standing right next to him. Then we assume that we can attack him. But if it's true, the target is more than one tile away, then we set the marker location, the target marker, and to the location of our target. We set visibility of the target marker. We find the path within the pathfinding array within the two tiles, just like before. In the player controller, we set has acted this turn to this current pawn to true, like in the player controller, and we set the array elements of the pawn array of the index we are leaving to empty, just like in the player controller as well. And the same thing with the pawn actor array. We remove the current pawn from the pawn actor array, and then we begin its movement, which is called inside unit parent. And then we set the current move of our current pawn to subtract the movement cost of the movement it just started doing, and then we clear the can move to array just to be sure. So that was quickly explained. I hope you could you could follow. If you haven't seen the player controller part, you should probably see that, since I explained stuff more detail there. So yeah, but if it is outside the move range, so we have to just move to the closest one. So then we check if the current move of the current pawn is greater than 0. So if we have a movement of 0 for the current pawn, then we just choose the next pawn because it can't move. But if it's greater than 0, then we find the reachable index closest to the target. And now I can explain this actually, which is in the grid manager. We do this by checking the path index array, the array holding all the indexes of our path. And for each of them, we check. We check the cost of that array element, and we keep going until we find one element that has a cost that is equal to or lower to the current move of the current pawn. That means that we can move to that index, and then we have found the index, the tile that we are able to reach. So that we set that as the target. The target is not a pawn, and then we set the marker and so on, and we move. So that's the AI controller. Quick and easy. So that means, ladies and gentlemen, that we are done with all our big gameplay blueprints. Actually, we have a few more here, but they are pretty simple. We have the HUD blueprint, which is very, very simple. It only has this little player turn text. here, which is, let's see, I worked so little with UI, yeah, which is a variable, so it can be modified in the graph, and it only has this simple event. So here first we get a reference to the tile spawner. I even had a little error here, but you know, I should add more of those. But yeah, and then when we run the event HUD turn toggle, which is fired in the game mode when a new pawn is selected and we have found out the faction. So it has player turn as an output. If it's the player turn, then we set the text block to say player turn. If it's not, then we set it to say enemy turn. So this is very, very simple. And then we have the grid camera, of course. I need to update this because some of this stuff actually doesn't make that much sense. I'm using the delta seconds all wrong. Many of the places I'm using them, but yeah, it works anyway. So these are pretty simple things, really. That when you click the rotate input axis, then you set the rotation of the camera actor. When you zoom, when you scroll, then you set the length of the let's see, of the spring arm. You can see here that there's a spring arm above the actor itself, and on top of that spring arm is a camera that's looking down. So when we zoom, the length of this spring arm is shortened or becomes longer. So that's what happens here in the zoom. And in panning, we simply we set the location of the grid camera. And then there's the follow cam. So if enable follow cam is set to true, and then we get the current pawn in the game mode, and we are not currently panning the camera, then we want to follow the current pawn. So in that case we set the actor location of this camera to be equal to the location of the current pawn, though we lerp towards that location, so it's a smooth, or rather smooth movement, though I should change these alphas. But yeah, that's the grid camera. Okay, and the grid manager hex is just the grid manager with a few things set up so that you automatically have a hex grid, but it's the same really, just a child actor. So that's that. Then let's look at the unit parent. So unit parent is the base unit, which all other units are based on. It works in and on itself just like this, or it should work. Let's see. So I set it up so that you don't need to have any animations or anything like that, so you can just change this, you know, with like a spaceship mesh or anything. You don't have to bother with animations, so it still works, still attacks, still takes damage, all that other stuff. And then all the animation stuff is added on these child actors. But yeah, so unit parents, let's see, so this one both has a construction script and an event graph. So in the construction script, a lot of stuff happens here when you drag the pawn into the viewport. So firstly, we set up the health bar. We created dynamic material instance, the health bar, and set a dynamic health bar material. This is so that it is possible to change the values of the material of the health bar, because the health bar is a pretty simple material. Let's see if I can find it here. Where's the health bar? There. Yeah, which has a percentage fill between two values of black and red, depending on yeah, it depends on this percent fill variable. So we change this variable, and then the material changes to reflect the current health of the unit. So we have to set up a dynamic health bar material so we can change that. And we always set the dynamic health bar material, or this scalar parameter value, the percentage fill value, to be equal to the current health of the pawn divided by the maximum health of the current pawn. Yeah. So let's see. So we get the grid manager. So yeah, didn't bother to make a reference here, though I use it quite a bit. though we use the grid manager for quite a few things, we use this vector to index interface, which is a very simple interface inside the grid manager. Let's see, you can see it when it's here. Actually, I have to go to the grid manager, it seems. Where's the interface? There. I want to sort these alphabetically soon, which simply takes a vector and gets it through the vector to index. You remember this old macro and outputs it. You should probably just put it within a function, so we didn't need that. But yeah. So it gets the location of the actor, and then it puts it into this function or this macro, and then it outputs the index. So that way, we always know when we move one of these. Let's choose one that's visible. When we move a tile around or pawn around, if you see here on index, it changes as we move, and that's how that happens. Yeah. So, and then we check, do we want to snap to the custom grid that we have? If we don't, we can just stop there. We don't want to do anything more, actually. If we want to, we check if this particular pawn ignores snap to custom grid, because that can be disabled here. So currently, you can see, oh yeah, it's not, yeah. So now he's snapping, right? Snap, snap, snap. And now he's not. So that's set up here. But yeah, so if we're not ignoring snapping to custom grid and snap to custom grid is true, then we wanted them to snap to the custom grid. So we get the index, which we got here, and we send through this get vector array interface, which takes the index, gets it through the old vector field array, and outputs that location. So that's the location of that particular index, which will always be in the center of that particular tile, and also adds the location of the grid manager. And then we break that vector. This is just and do a line trace. So we do that to check if the tile that we're moving the pawn to has a different height, and in that case we want to set the pawn at that particular height instead of like at the Z of 0. So yeah, and then we set the location of the custom grid anchor to be equal to the location we now found. And the custom grid anchor is, let's see, is the one that's here. That's an anchor that's always placed in the center, and then anything that's attached to the custom grid anchor will be which in this case the skeletal mesh is and the health bar is, will be moved to the center of the tile. Right. Okay. And do we want to place the actor at the anchor? Yeah, this is so that we can now, you see, you can move the actor back to where the anchor is. If we want to do that, then we set the actor location of the custom grid anchor. We set the actor location of the actor of the self, the unit, to the location of the custom grid anchor, and then we set place actor to at anchor to false. So we don't loop that forever. That's in the construction script. Then for the event graph, we have a lot of things. So first we set up our references like we've done many times before. This time for the game mode and the AI controller. And let's see, for every tick we want to rotate the health bar to face the camera, so that is always facing us. So that's a simple set world rotation where we get the location of the camera manager and find the look rotation between that and the health bar. So that's simple enough. Then here we have movement, which is done every tick, but we have a gate here. So it's opened if we want to begin our movement. If not, it's you enter but it's closed, so nothing happens. Now when we begin movement, which if you can remember is fired from player controller and AI controller respectively, and it also gets these inputs: stop X tiles from target and attack on end, which is set in the player and AR controllers. So we have those stored here. So attack on end is true if we have clicked an enemy that we can move to, or if the AI can move to and attack an enemy. And stop X tiles from target is also set if we click an enemy, because we want to stop one tile in front. So yeah, so if it is open, we want to move, and then first we do one thing that we only do once, though we reset it when we end movement. And what we want to do once is to get the spline length of the path spline, and we set that to the current spline distance. So the current spline distance, that's where on the spline is the pawn currently located. And the length, that is, since the spline starts at the target and ends at the start position, that means the start position is at the location of the length, the entire length of the spline. So that's where we want to start. And we set the unit path spline, so that this is a particular spline that is contained within the unit, is set to be the same as the path spline in the grid manager. So after we've done that, then we do that the thing we want to do every tick. So we set idle to false. We don't need to do that every tick, actually. I should move that up here. Yeah, but yeah, it doesn't really matter. So is the pawn, but I will change it. Is the pawn target outside its move range? So we check that to check the length of the path index array compared to the current move. So yeah, let's see. Actually, that might not be necessary anymore. I'll have to look into that as well. But yeah, so I think this should always fire false now. I might be wrong. But in any case, we stop movement if it has reached the end of the spline, or the node before the end, if the target is a pawn. So we get the path spline, and we check the distance along the spline to that particular spline point, and usually this will be equal to 0, which is the target. So if we get point index 0 and we find where is that on the spline, which is actually on spline distance 0, if it is true, then we want to stop the pawn. If it is not true, that means we have not reached our end target yet, and we want to accelerate and move the pawn along the spline. And so we want to keep accelerating movement speed until the max speed is reached. So we accelerate the movement of the pawn, so there's a smooth movement when we start moving. So we check if the max speed of this pawn is it greater than its current speed. If it is, then we want to keep accelerating, right? So if it is greater, then we want to add the acceleration every tick to its current speed until we reach its max speed. If it is already at its max speed, we just want to keep moving at that speed. And then we set the current spline distance, like the position the pawn is currently on the spline. We want to increase that. And we increase it by getting the current speed and multiplying it by delta seconds, and multiplying that by the tile bounds of the grid manager. So yeah, the speed of the pawn is dependent on the size of the grid. So this is so you can resize the grid and use the tiles you want, and the movement across tiles will stay pretty much the same. But yeah, and then we subtract that from the current spline. This is, remember, we started at the length of the spline, the absolute max point of the spline. So we subtract that value, the current speed value, until we reach the end. And then when we change the current spline distance, we want to set the actor location and rotation of our pawn to be equal to the current spline distance, location and distance along that spline. Yep. Let's see. Where are we? There we are, and there. Okay. So when we have reached our destination and we want to stop, and then we set the current speed to 0, and we set the actor location to be equal to, let's see, the index of our endpoint, which could be 0, or if we want to stop X tiles from the target, it will be a different number than 0. But we should be stopping there anyway, and but just to be sure, we make sure that the pawn is at the exact location we want it to be. And then we set the index of our pawn to the index where we ended up staying. And then we set the array element of the pawn actor array to the faction of our current pawn at the new index. So we add its faction to the new index. And we also add the pawn itself to the pawn actor array at that index. So now the arrays are updated so that we know that the pawn in question is on the new location. And then we fire the end movement custom event, which is here. Earlier here we would just close that gate, which stops the tick from firing the movement event. And after that, are we attacking on end? If we are, then we attack the victim on the end of our path index array. If not, then we set the visibility of the target marker. We make it invisible because we have reached our destination. And if it's, let's see, if it's the player turn, after we have moved, we want to activate that player again. And if it's the AI, we want to activate that AI again to see if they can still do anything more. As you saw in the player controller and AI controller, if they can't do anything more, then the next pawn is chosen inside those blueprints. So yeah, so attack victim, let's look at that. So if we're attacking someone, that's here, straight beneath in the same event graph. So we attack the victim. The input of the victim was whatever pawn was standing at the end of our path index array. So we attack this guy. First we set the marker location of the target marker to the same location of the victim we are attacking. And we set the visibility to true. And then we set the rotation also of our actor to be facing the target he is attacking. So we get the look at rotation between the actor and the target he is attacking, and set it as his new yaw. And then on our victim, we set him to receive damage. So we get the damage of our current pawn, and also the animation damage delay. This is how long from the attack starts until damage is dealt, which should be set depending on how your attack animation looks. So we do the receive damage event. So this is fired actually on the target, even though it's in the same event graph. This will be fired on the target. So here we delay for a duration, which can be set custom depending on your animations. And then we set the current health of the victim to be equal to its old current health minus whatever damage was dealt. And then we set the scalar parameter value of its health bar to be equal to now its new current health divided by its max health at the percent fill value. And we set the marker visibility of the target marker to be false. After we have attacked, we don't want to see the target marker around the victim anymore. And then we choose the next pawn. I think this should maybe be moved to somewhere else so that you can do stuff like area attacks and do damage without ending your turn. I'll change that in a later update, I think. So you'll probably see a little annotation up here soon. Okay, and then if the current health of the attack of the victim is lower or equal to 0, that means we want to kill it. So if it is, then we set the visibility of its health bar to false. So the health bar disappears. Then we set the array element of the pawn array at its index to empty because there's no pawn there anymore. And we also remove it from the initiative order. And we remove it from the pawn actor array. And then we call destroy unit, which also has an death anim delay. So the animation of death starts at once, but this is how long we wait until we destroy the unit. So if you always want to have the corpse laying there, you can set this to, well, yeah, infinite, I guess, but yeah, it would be better to change that up, I think. Okay, and destroying the unit is simple. We have a delay, and then after that we destroy the actor. So that's all of that. But now let's look at the animation bit. Let's see. So for animation, let's look at pawns, and then we'll look at any one of these. So let's look at unit pair melee. So it does only a few things. So it runs the tick event, which is on unit parent, and it runs the attack victim. It runs all of the functionality that is within unit parent, but it has some additional stuff as well. So on the tick, it also runs some more stuff. If it is idle, let's see. So the moment it has become idle, then we want to stop its move animation. If it's not idle, then we want to move to play the move animation. Let's see. So then we get the animation instance of its skeletal mesh. We cast it to the animation blueprint parent, and we run its move animation. So that's inside the animation blueprint. Yeah. Let's see. And as for attacking, we want to also cast to its animation blueprint and run the attack animation. When it's dying, we want to cast to the animation blueprint and run the death animation. So that's basically all there is to that. But yeah, so this interfaces, of course, with the animation blueprint parent, though there are different animation blueprints for different animations. So for the move animation, we cast to unit parent to find its current speed, and then we set the speed value of this animation blueprint to whatever is the current speed of the unit parent that has this animation blueprint within it. So if the speed is 0, we want it to stand idle like this, right? But if it's higher, we want it to walk or run or whatever. And if we run the attack animation event, then we set attack to true, death animation set death to true. So these will check branches that will fire either of those animations. And then we have an animation notify at the end of the attack animation that stops the attack later. So we have that in the state machine here. So in the state machine we have the idle walk run, so we get the speed value that we just set, and we run it into this blend space. I mean, I have described this before in the animation part, so maybe I won't describe it too much here. But yeah, that's and the speed value between 0 and 600 decides which animation is played. And yeah, then we check this: is death set to true, is attack set to true, then we want to run the punch or the death animations. And after punch has run, let's see, so we have the attack, then we check for this notify event here. So when that is run, it checks this, so it goes back to the idle walk run part of the blueprint. So that's very quickly, but I've already described this in a previous video, so I won't go into that anymore. That's that for animations. Okay, we're actually getting pretty close to the end, I think. Though we have one more thing: the tile parent. So the base of all tiles also has a lot of its own stuff, though a lot of it is the same as in the unit parent. So it has some other stuff as well. So also here it finds the index on the grid, just like in unit parent, and it checks if it should snap to the grid, and all of the same stuff, actually, finding the height, setting its location, should it be placed at the anchor. All of this is identical to unit parent, but it also has this stuff. But yeah, I think I won't go into this since it's pretty complicated. The whole functionality that makes all the static meshes turn into instant static meshes. Because let's have a quick look. can hear my skepticism, I'm sure. Yeah, this is to replace actor meshes with instances, and there's a lot of custom small. Yeah, I can make another video of this if people are particularly interested, but I actually kind of hope not. But yeah, it was fun to make though, but it's kind of tricky to explain. But it has some pretty huge performance gains for some stages at least. Okay, let's see, do I have anything more? I got the HUD, I got all of these. I think we're actually there. Yeah. So that's that. I'm sure that there's a lot of stuff that I could have explained better. Some stuff I explained for too long. But yeah, I've done my best in any case. Tried to keep it like reasonably deep, but not too much of a good thing, I guess. But just ask anything that's confusing in the comments below or in the forum thread. And I will answer as quickly as I can, and I will try to clear up future confusions or any of those confusions in annotations in this video that we'll add in the future. And when I update this toolkit, as I do quite regularly, then I will add annotations to note where there have been done some any changes. But I hope that things are in finished state enough that I can keep this video and just add comments like that. So I hope you enjoyed this video, and if you managed to watch it from start to finish, I commend you, and I hope you I wish you luck in your project, and hope this will be useful in letting you make whatever turn-based strategy games you want, because I want to see lots of new cool turn-based strategy games come out of Unreal Engine in the future, and that's why I made this stuff. So well, yeah, that's it for now. Bye bye.